Have you ever stopped to wonder how the video you're watching right now is getting to your screen? I mean, there are no wires, right? It's all thanks to these invisible waves carrying information all around us. In this explainer, we're going to pull back the curtain on the fundamental trick that makes it all possible: how we teach simple waves to speak the incredibly complex language of computers.
Seriously, just think about that for a second. There are no cables connecting your device to the server holding this video. So how in the world does your phone take the digital ones and zeros that make up this explainer and turn them into a signal that can just travel through the air? That is the exact puzzle we're going to solve today.
All right, let's dive right in. To really get how waves can carry data, we first need to understand their most basic property, kind of like learning the alphabet of their language. And that alphabet starts with one single crucial concept: frequency.
So frequency is basically just how often a wave pattern repeats itself. The easiest way to think about it is like the pitch of a sound. A low, deep bass note has a low frequency, while the really high, shrill note has a high frequency. We can measure this really precisely, and more importantly, we can control it.
And you can really see the difference right here. The low-frequency wave on the left is all stretched out, kind of lazy, with fewer peaks and valleys in the same amount of time. That's our slow, deep bass note. But look at the high-frequency wave on the right. It's way more compressed, with tons of cycles packed in. That's our high-pitched soprano.
So, and this is the whole point, if we can control the pitch of a wave, we can start to assign meaning to it. We can just decide that a low pitch means one thing and a high pitch means something else entirely. This act of embedding information into a wave by changing its properties, well, that's the magic trick. It's called modulation.
Okay, so let's see how this basic alphabet builds into a real communication system. We're going to start with the simplest digital language there is: binary. The good old language of ones and zeros. The process itself is wonderfully simple. We just create a little code book with only two rules. We decide that the number 1 will be represented by our high-frequency note, and the number 0 will be our low-frequency note. So, to send a message, the transmitter just plays the correct note for each bit it needs to send. This little table shows the direct mapping perfectly. When the receiver on the other end hears a high-frequency tone, it knows, okay, that's a 1. When it hears the low-frequency tone, it writes down a 0. And boom. Just like that, we've taught a wave to speak binary. Now, this technique has a fancy-sounding name: binary frequency shift keying, or just FSK. But let's break it down. Binary because there are two states, 1 and 0. Frequency shift because, well, that's exactly what we're doing. We're shifting the frequency. And keying is just an old-school term for sending a coded signal. See? Not so intimidating. Now, a 2-word vocabulary is great and all, but it's not super efficient if you want to send, say, a high-definition video pretty quickly. To speed things up, we need to give our wave a much richer vocabulary. This really is the core challenge in modern digital communications. How do you cram more information into the same amount of time? Can we actually teach our simple wave to communicate more complex ideas than just a single 1 or a single 0 with each little burst of signal? And the answer is a resounding yes. And the solution is to stop thinking one bit at a time. Instead, we can group bits together into more complex symbols. This lets us send way more data with each signal we transmit. Okay, check this out. Instead of just 2 frequencies, let's use 4. Now we can give a unique frequency to every possible pair of bits. So 00 gets the lowest frequency, 01 gets the next one up, and so on. All of a sudden, a single tone is communicating 2 bits of information at once. We've just literally doubled our data rate. This is the basic idea behind something called M-ary FSK, where M just stands for the number of frequencies you're using. But there's a trade-off, right? There's always a trade-off. Every new word in our vocabulary needs its own unique frequency. Think of the radio spectrum like a highway. The more frequencies you use, the more lanes you need. This width is what we call bandwidth, and that radio highway only has so many lanes. It's an incredibly valuable and limited resource. So far, we've been talking about this in a perfectly quiet, clean environment. But the real world, it's chaotic, it's noisy. So let's look at how these techniques adapt to survive out there in the wild. I mean, real-world signals are just swimming in a sea of noise. You've got interference from other Wi-Fi networks, from microwave ovens, you name it. So if we're sending our ones on one specific frequency, What happens if your neighbor's powerful signal starts blasting away on that exact same frequency? Well, our message just gets drowned out. It's gone.
To get around this, engineers came up with a really clever trick called frequency hopping spread spectrum. The idea is simple. Don't be a sitting duck. The transmitter and receiver agree on a secret hopping pattern ahead of time, and then they just rapidly jump from one frequency to another together. It's actually the same basic principle that keeps your Bluetooth headphones connected in a busy coffee shop.
So this is what that hopping looks like in action. For just a few milliseconds, the signal uses one frequency. Then, bam, it hops to a totally different one. Then another, and another, hundreds or even thousands of times every second. So if one of those frequencies happens to be jammed by interference, who cares? We only lose a tiny little piece of the message before we've already hopped to a clear channel. It's incredibly robust. And this is absolutely a proven technology. The source material points to an awesome early example, the Tactical Transmission System, or TETS. It was built for military satellite communications, where, reliability and security are everything. By hopping between frequencies up to 3,200 times a second, think about that for a second, it created a signal that was incredibly tough to jam and really, really hard to intercept. So from these simple high and low tones all the way up to these complex, super fast hopping patterns, these fundamental principles of frequency modulation are actually more important today than they have ever been. This quote right here really just captures the whole thing perfectly. Frequency modulation isn't just some abstract theory in a textbook. It is the engine of our wireless world. It is the essential bridge that connects the digital realm of ones and zeros to the physical reality of the waves that connect us all. And that leaves us with a final and pretty fascinating question. With billions of new devices coming online, everything from smart cars to smart toasters, all of them needing to talk wirelessly, the airwaves are getting incredibly crowded. The great challenge for the next generation of engineers is figuring out how we build on these foundational ideas to orchestrate a world where everything can talk to everything else, all at once, without getting in each other's way.